Today's lesson is on statics, sections 9.1 and 9.2 in the textbook. This will be our last section of notes that we do in our unit with rotation. And truly, this doesn't deal as much with a lot of the angular quantities that we've been talking about the last few days, but it does deal with net torque, and it brings back net force and some of the ideas we had in our forces unit dealing with things like equilibrium and balancing things out so that an object does not accelerate. And in this case, we're going to take a look at that from a little bit more of an engineering perspective and see how we can solve some problems to make sure that things that are designed to not move will actually, in fact, not move and stay stationary, which is where the term statics comes from. So the first thing that we need to have for this is that there are two conditions that have to be met for something to remain in equilibrium, which means all of the forces and torques on it will not cause it to move or to rotate. So we have two conditions that have to both be fulfilled in order for an object to stay completely stationary, because you have not only the motion of forces that can cause something to move up and down, you also have torques that can cause rotation. And so you need both things to be balanced in order for an object to truly stay completely at rest, which is what you want when you design things like a building or a structure. So the first condition that we have to have is that the net force has to be zero for that particular object or beam or structure. Mathematically, we would write that as F net equals 0. You add up all the individual forces acting on something, they all have to come to balance out to be 0. What this also means is that if the object is initially at rest, it has to then stay at rest because there's no net force that would cause it to accelerate. So if object is initially at rest, it will stay at rest because it can't start moving anywhere, accelerating anywhere if the net force is 0. And the other thing that is important to keep in mind here is that that condition must be true in all dimensions. Now we're only going to deal with potentially up to 2 dimensions, x and y, but if we're talking 3-dimensionally, that would include x, y, and also z. So you'd have to look at the 3 different possible dimensions, and it would be true of the components in all 3 dimensions. And like I said, you're not going to be faced with any problems that have more than 2, but if you have an x direction and a y direction involved with your forces, in order for the overall net force to be 0, all of the x component forces would have to balance to 0, and then all of the y component forces would also have to balance to 0. The second condition that has to be met is that the net torque also has to be 0. And this is what deals with our rotation part of it, and we would just write that as net torque equals 0. All of our individual torques have to be balanced out in order for that condition to be true. And then the follow-up piece to that is that this means if the object is not rotating initially, it will not begin rotating either, because if there's no net torque, there will be no angular acceleration, which means the object will not start rotating if it was put at rest. Now, the reason both these have those statements about initially being at rest or initially not rotating, that's because when you build a structure, especially obviously an engineer, you set it up to not move. So you don't want it to move anywhere. It starts stationary. You want it to continue to remain stationary. And so we have those conditions that need to be met, and with the also follow-up ideas that you start it at rest. Otherwise, it is possible to have something have a net force of 0 and still be moving at a constant rate because there'd be no acceleration. There'd still be no net force. But we don't want these things to move in statics. We want them to be completely stationary. So we have a couple of examples to take a look at these ideas. So here's our first one involving a couple of kids on a seesaw. And so we have a board that is set up here, centered on a pivot point, just like a traditional seesaw would be. And we have 2 kids, Alvin and Simon, who are going to be sitting on there. You can see their masses indicated in the problem. and Alvin sits 2.5 meters from the pivot point on one side. Simon has to sit on the other side, obviously, to try to balance that out. Where exactly is Simon going to have to position himself relative to the pivot point in order to completely and perfectly balance everything out? In other words, we want everything to be balanced in terms of the rotational torques in this case. So those would have to be 0. And then the second question is how much force is needed at the pivot point in order to support the entire system. So both people and the board itself would have to be included with that. So we will use both conditions, but individually, one for each part of this problem to be able to solve it. So as we get going, the first thing that we're going to look at is our question about where does Simon have to sit in order to balance it. And the picture does help a little bit with understanding what's going on. So we have Alvin sitting on one side. We'll say he's over here. So this would be the mass of Alvin times G. That would be your force acting there, his weight. Somewhere over here is going to be Simon. So we'll say ms for the mass of Simon times G. And we know that Alvin sits 2.5 meters from the middle. Where does Simon have to sit in order to balance everything out? So this part of it is just a simple torque problem based around this pivot point in the center. What is going to be the necessary distance here, or radius, in order for this force and its torque, rotational force, to balance the torque from Alvin on the other side? So our first condition would simply be that the net torque has to be 0. We know this. That means any torque to the left, which would be from Alvin, would have to be balanced by any torque to the right. Those are the only two things causing torque, because the other force, the one of the board, would be downward here in the middle. So mass of the board times G. But that's acting at the pivot point. So its radius is 0. It does not provide any torque. And then the upward force from the pivot itself, we'll call that FP, is going to also be acting there. So that won't impact the net torque part of this either, because it's also acting at the pivot point, which would have a radius of 0. So as we look at it, we only have Alvin and Simon that we have to deal with, and we know that the force would be their weight. So the force times radius for Alvin would be mg times r, and then same thing for Simon, mg times r, and then we can fill that in. So again, this is coming from the idea that torque is equal to force times radius. The sign of theta doesn't matter because theta would be 90 with the way that these are drawn. So that would be 1. So it's really just the force of their weight times the distance they're sitting from that middle. So the mass of Alvin, we just fill things in, is 30 kilograms times 9.8 times his distance of 2.5 meters equals the mass of Simon, which is going to be, 25 kilograms times 9.8 times the radius we don't know. And we're solving for that radius. So as you rearrange this, you divide by 25, you divide by the 9.8 to the other side, and you would get then a radius for Simon that would equal 3 meters from that center pivot point. For the second part of the problem, how much force is needed at the pivot point to support everything? For the net force to be 0, that means that all of the upward forces, which there's only one, would have to equal all 3 of these downward forces in order for it to be supported. If it didn't, the seesaw would break right here where it's trying to support it, because that force would be overloading it. So this means our upward force, the force at the pivot point, which we called FP, has to be equal to the mass of Alvin times G, so that's the weight of Alvin, plus the mass of the board itself times G, which is the one acting here in the middle, plus the mass of Simon times G, the weight of Simon. So we have the weight of Alvin, the weight of the board, and the weight of Simon. And they have to be equaled by the force at the pivot point. So this one's set up nicely for us to be able to solve. We just have to fill in all of the masses. So 30 times 9.8 plus 4 kilograms for the board times 9.8 plus 25 kilograms for Simon times 9.8. And all in all, when you crunch those numbers in the calculator, you get 578.2 newtons upward, acting at that center pivot point that would be this force here in the diagram. That has to support all of these that are acting downward. So we see both conditions, net torque and net force, used in this problem, but they are used individually in this case. In a lot of our statics problems, you're going to not have the chance to necessarily look at the two things individually, but you're going to have to use both of them together to set up a substitution or a system of equations to be able to calculate what you need to find. So here we have an example like that, where we have a uniform horizontal beam in our diagram, 1,500 kilograms. It's 20 meters long from one end to the other. So that means this whole overall distance here is 20 meters. And we know that there's a printing press sitting here, so that force would be right there. And this would be the mass of the printing press times gravity. That would be the weight of it that would be acting at that point. The beam itself in this case is also significant. It's 1,500 kilograms. And because it's uniform, that means that the weight of the beam would be pulling downward directly at the center of gravity. That's how we define center of gravity. So this would be the mass of the beam times g. So that gives you the weight of the beam. So here's our two downward forces. And the things that support that are coming from these support columns on the end. So we have one on the right end, one on the left end. Those two upward forces are the ones that are being asked about in the problem, the forces being provided by the support columns. So we'll call these FA and FB to be able to distinguish between them as we set up the problem. Now, hopefully you can understand by looking at the picture. I did not draw the forces proportionally in any way at all, but just to show the locations is what I'm using the arrows for. But with the printing press offset to the right-hand side, this force at column B will be larger than the one at column A because there's more weight sitting towards this end. So a couple other things that we can put on here would be the distances that are involved. So we know that the printing press is 5 meters from this right-hand side. And we also know, because this has to be centered, the weight of the beam itself, and the total length of the beam is 20 meters, that would put it 10 meters from either end, whichever way you want to draw it, but I'll put it on the left side just because it's a little less busy there. But it has to be perfectly dead center. So that gives us enough to go with to begin. So the first condition that we're actually going to look at this time is the net force condition. So if F net equals 0, that would then mean that we have the two upward forces, FA plus FB, have to be equal to the downward forces, which would be the mass of the beam times gravity, plus the mass of the printing press times gravity. And that would have to then be a true statement in order for the net force to balance to 0. In other words, in order for this whole structure to be stable, this would have to be true. We don't know what FA or FB are yet, but we do know these other things, so we can fill those in. The mass of the beam is 1,500 kilograms times gravity is 9.8, plus the mass of the printing press is 15,000 kilograms times 9.8. And if we calculate the right-hand side, we might as well simplify that down as far as we can. We know that the total sum of FA plus FB would have to give us 161,700 newtons. And that's as far as we can go with that equation at this point in time. So in order to get a second equation, we now need to use the net torque condition. So net torque is 0. Now as we look at this diagram, we can do something here through some common sense that will make our solving this way easier. So what we're going to take a look at is, where do we put the pivot point? We get to choose this time. With the seesaw, it made sense to keep it at the actual physical pivoting place of the seesaw board. In this case, this object is not moving. It's not tipping one way or the other, that we don't want it to anyway. So we get to pick where we measure the pivot point. Well, since we don't know FA or FB, it makes a lot of sense to put our pivot point at one of these locations. Because when we set up the torque, if the force is at that location, its radius is 0, therefore its torque is 0. So we'll put it right here. FA will be our pivot point for 0. So that means we don't have to worry about that force when we do the torques, we just have to worry about these other three. And the two weights, the weight of the beam, the weight of the printing press, want to turn this to the right or clockwise, and FB wants to turn it back the other way, counterclockwise. Those have to be balanced because they're separate rotational directions. So that means the torque from our FB column has to be equal to our torque from the weight of the beam plus the torque from the weight of the printing press. There's a lot of subscripts there. So the torque from the beam would be FB times the distance from the pivot point for that. And our weight of the beam is MB times G times the distance for that from the pivot point, and mg for the printing press times the distance for that from our pivot point. So now we fill in what we know here. FB is going to be a distance of 20 meters. It's the full length of the beam away from our pivot point over here. And then the mass of the beam is dead center, so that's 10 meters away. So that's going to be 1,500 times 9.8 times 10 plus we have the mass of the printing press, 15,000 times 9.8, and it is 15 meters from the left-hand side here. So it's 5 meters in from the end of the 20-meter long board or beam. So now we can solve this. We can crunch everything on the right-hand side. Then we have to divide by 20, and we will get an answer for FB of 117,600 newtons of force on that support column. Now that we have FB, we can, of course, go back over here, plug that in for FB, and then solve for FA. So it becomes a really simple substitution in this particular problem. And once we solve that, we get a force from support column A that is equal to 44,100 newtons. And that's everything. That's both things the problem asked us to find. And we have done what we needed to do using both conditions for the static equilibrium that we have. So now I have one problem for you to try on your own. So you can work this out on your own first. Here's, whoop, I'm going to move the camera maybe a little bit there. Get everything in. Okay, so you have a cantilevered beam, which means it sticks out over empty space on that right-hand side. And you have two support columns, and we call those FA and FB again. And then the mass of the board itself is in the middle of the board here, or the beam, and in this case the beam is a total of 50 meters long, and you can see how some of those other measurements are stacked up. You need to solve for FA and FB using the same process that we just did in the previous example, setting up the two equations with one with net torque, one with net force. So at this point, I would ask you if you want to try this on your own, pause the video, give yourself some time to work through it, see what you get. And in a couple seconds here, I'm going to reveal the answer anyway, so if you don't pause the video, you're about to spoil everything. And so here's our solution to that particular problem. So I have set up the two conditions, so you can see net force and net torque. So the net force side of things, FA plus FB, has to equal the weight of the board that's downward. And so I've set up from our diagram and from the original diagram I showed you here as well, same thing but a little bigger. I indicated that FA and FB are both pointing upward. So I would treat this as the two upward forces have to equal the downward force that I have here. So that means FA plus FB equals the weight of the board. And so we come down here, we can find the weight of the board, and we see that's an 11 there. It kind of looks like a 16. 11,760 newtons for the total force that both things have to provide. So in order to get more specific than that, we need to go to net torque. Net torque equals 0. I picked the rotation point to be at the left-hand end again at point A, so that wipes that one out for torque since its radius would be 0. And we only have to worry about FB and then the weight of the board in order to solve this. And so that's what I have here. And I actually set them up on the same side and equal to 0. You could also have said FB times 20 equals mg times 25, and that would be the next step essentially from here. And so as I set that all up, I solve for FB, I get 14,700 newtons. I come over here, I plug that in for FB in the equation I had with net force, and when I solve it, I get a negative. I get negative 2,940 newtons. So what does that negative mean? Well, it means is that I had set up FA to point upward in the original diagram, but when it comes out negative, it means it's actually going the opposite way. It's actually pointing downward, which does make sense when you think about it, because if you had this board, my pen is the board, and it's two support columns here, the mass or the weight is trying to pull it off like this. So the inside support column, which was FB, has to provide an upward force, but on FA, you actually have to attach it with a bolt or something like that to hold it down so that it doesn't tip over like this when gravity is pulling on the center of gravity of the beam. So FA should actually be downward, and even though you might have known that or suspected it going in, I wanted to set it up intentionally to go the other way to show you how you recognize what happens when in a situation maybe you don't know exactly which way the force is acting and you guess. It doesn't matter as long as at the end you've been consistent with everything, because when that negative comes out, you realize, oh, okay, that means it's actually going the opposite way. That means FA is actually pointing downward and not upward.